Okay, so by the end of class today, we should be able to find how the interference of sound, the reason that sound have interference because sounds are waves and wave has this effect of interference, right? And this will actually create these things called beats, which is actually, I will just actually show it to you guys in a second. And I also how to calculate the speed of a train just by listening to it, okay? This is how we actually find out how fast things are. The effects of beats, I'm actually gonna demonstrate to you right now. And then we'll see how that works mathematically afterward. So I have in my hand two tuning forks that are the same frequency. I think this is written, it's 440 Hertz. So that's like a, I think that's, I don't know what note it is. Usually there's a student who knows what notes are, but I think it's like an A or B or some letter, okay? But this is what it sounds like, 440 Hertz. You know, and then the other one, whoops, it's a little bit rustier, but still works. I should point this towards you guys. Right, it sounds the same. It's the same tone, right? This one's also 440 Hertz. Okay, what I'm going to try to do is I'm going to ring both at the same time. So that's why I need to put it on the table. Okay, so you play both sounds that are exactly the same frequency. It's the same sound. Okay, what I'm going to do, I'm going to change one of the frequency with a little silly putty situation. Let's put on this one. So I'm adding a little bit more mass to one of the tuning fork. And let's see what happens. Okay, so this one, oops, I'm just hitting it too hard. Okay, I'm trying to hit both at the same time. Okay, so here we go. You guys hear anything happening? Maybe I don't hear it because I'm on the other side. No? Okay. Well, it's actually the interference of both sounds at once. Okay, I'm not trying to, it should be a pretty obvious effect. Let me actually move it over to Anthony where maybe the corner is a little bit aiming towards people. It's like a wong, 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 wong sound, right? Okay, I'm gonna decrease the mass I made on this guy a little bit. Just remove a little bit of silly putty. Okay, let's see if we can hear a bigger difference. Right. This is actually known as beats. Okay, and this effect is due to the interference of the sound waves coming from both of these tuning forks, but one of them I modified to have a slightly different frequency. Okay, and let's see how we can actually see this with math, right? Well, physics, but with a little bit of math involved because we have to deal with these sines and cosines equations, okay? So in this section, for whatever reason, the book decided to use cosine to represent waves instead of sines. But you know that cosines and sines are just the same function, but they're just shifted away from each other, right? By pi over 2. So I think the reason is that they have the better trig identities to deal with this particular effect. Okay, so let's say, right, we have one wave, right, some y1, okay, and that wave, can be written with this some amplitude, some times a cosine, right, of some wave number 1 and some frequency 1. Now we're going to deal with two different, right? Remember, wave number k is related to the wavelength, right? Frequency, well, frequency is frequency because we put the 2 pi's in here, so that's fine. Okay. All right, and then we're going to add to that, superimpose that, or interfere these two waves, okay, with another wave called y2. It has the same amplitude, let's say, okay, and it's cosine of k2, which is related to wavelength number 2, right? So it's different wavelength, and different frequency. And that's what's actually important. In order for them to have this 111 effect, they have to have a slightly different frequency. Okay. So now we're going to use more trig identities. So this is lambda 1. This is lambda 2. We're going to use more trig identities, where if you add two different cosine functions together, it's the same thing as twice that function, twice times those two cosine function with the plus of the arguments divided by 2 and then minus. Okay. And so let's go through the little bit of trig identity math. Okay. When you combine these two waves together, what happened is that the u, so we're going to make this piece u. So u is basically equal to k1 times x 2 pi f1 times t. And then this piece is going to be v. Okay. V is going to be k2 times x minus 2 pi times f2 times t. Okay. So right away, what you can see is that, well, when you have u plus v, okay, right, you're actually taking this number and adding them together, right, and dividing by 2. That's the same thing as just taking the average of it, right? When you add two numbers together and you divide by 2, that's taking the average of it, right? So if my age is 43, your age is, I don't know, 22, right? You add those two ages together, you divide by 2, you get the average age, right? Whatever that is, okay? So what happened is that this first piece here just become whatever the average frequency is, okay? The other piece is the difference between the two, right? When you subtract these two guys, okay, you actually have the difference of the two frequencies, F1 and F2, okay? If you actually go through all the, the multiple steps of trig identities and stuff like that, you actually will be able to derive this equation. But right now, we just want to kind of see where this little piece comes from and where this little piece comes from, okay? Okay. Now, what will happen is that you have two different cosine functions that are multiplied into each other, right? When you multiply two cosine functions together, you get something that looks like this, okay? This blue line here, the amplitude gets doubled, but then, right, the regular frequencies you have in there, right, F1 and F2 are going up and down, up and down, up and down, up and down. This is actually the average part, okay? Okay, this wiggling is F average, okay? But you can see that there's these, what we call lobes, right? These lobes around here where the sound suddenly goes louder, quiet, loud, quiet, quiet, loud, quiet, right? Bigger amplitude, right, means more power, right? In fact, the amount of power is the amplitude square, right? So therefore, this is the loud part of the sound. Oops, I can't spell loud, right? This is quiet, right? And loud, quiet, okay? This happens at a much lower frequency because this envelope here is actually characterized by the difference between the two frequencies, okay? So on that little tuning fork, what I did is that, well, this tuning fork is 440, but then by adding a little bit more mass here, I lowered the frequency by maybe like 2-3 hertz, okay? And therefore, right, the average frequency is still about 440, but this envelope is coming out at about 3 hertz, okay? That's why you hear that 1, 1, 1, 1, 1, 1, 1. That's why you can actually tell it gets louder, quiet, louder, quiet, louder, quiet, right? 3 times per second. Does that make sense? Why this graph actually represents what we actually hear in real life. Okay? Everyone okay? So this is known as the beat frequency, right? And to calculate the beat frequency is actually a pretty simple formula. So this is actually the one you want to use in the test or something like that. But the beat frequency is just the difference between the two frequencies. Okay, so if I have 440, right? If I was able to lower the frequency of this tuning fork by 3 hertz, that means it's going to be 437 instead. The beat frequency you hear, right, by this rung, 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 rung sound, right? That's 3. You can actually completely predict how, by modifying the frequency of one of the tuning fork, you can actually completely predict how fast that rung, 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 rung sound is going to be created. Okay. So when you have, let's say you're in an orchestra, right? And a lot of times when you play the instrument by yourself, right, it sounds perfectly fine because our ears are actually not very good at differentiating, 440 hertz with 437 hertz, right? So 3 hertz is not that big a difference to us. But when you play multiple instruments together in an orchestra, if one of them is out of tune by 3 hertz, you will hear this wong, 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 wong sound. Okay, so it's really obvious when something is out of tune with one another. Okay, that's why whenever people show up to these big orchestra events, right, all of the instruments has to be tuned to be exactly the same frequency. Okay, otherwise the audience is going to be like, hearing this wong, 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 wong sound all night. Okay. By the way, this is actually how they also tune piano. So you would think, well, it's really hard for me to be able to figure out, oh, is this piano, tuned to exactly 440 hertz, right? But by having a tuning fork next to it, and you play the same key on the piano, if you hear the one, 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 one sound, right, that's when you know the piano's out of tune, right? So that's a way to apply that. Okay, but the end question is that's how you calculate the beat frequency. Okay. Any questions about this section? Okay. Good. Okay. Last section we'll cover for this class is the Doppler effect. And this is once again something we get to listen to. Unfortunately, I don't have a train that I can bring to class that'll give you this effect, but we can play the little video on it. So hopefully the sound is not going to create a problem. Let's see if the sound's okay. Sorry, hold on. I always like to go to the headphone first. Okay. Let's see if the sound makes it through this time. Okay. So what I want to do is just, we're going to listen to this multiple times. Just listen to the train. We're making sound. Sorry. Okay. Just listen to it once. We're going to listen to it again. Okay. This time, try to see if there's any difference you hear before and after the train passed by the person taking the video. Okay. Go back. Anyone wants to tell us what they heard? I mean, like, what did you hear? Let's just say what everyone heard. Anyone from this side of the room? You heard a train. It made a sound with a horn, right? What else was there? Right. It got louder as the train got closer, right? But then as the train just passed by the person taking the video, was there something that changed besides how loud it is? Okay. Oops, let's go back to the beginning here. Okay. If you were to make that sound with your own voice, how would you make that sound? Right. It's deeper right after it. So this is what when I was a kid called the wee woo sound, right? Wee woo, right? So wee is a higher pitch sound, woo is a lower pitch sound, right? When we speak. So as the train approach, right, is making the wee sound. Right after it passed by you, it made a woo sound, right? So somehow the pitch of the train change, right? It went from a higher frequency to a lower frequency, okay? This is actually known as the Doppler effect, and we can actually study this. These diagrams are actually not from your textbook because I found your textbook not to be that great for that. But let's say you have a source of a sound. This is V S, right? Sorry. You have a source of sound, right, that is standing still, and you are here listening to that sound, right? What we want to think about is that, well, as the sound gets created, it propagates outward, right? At time equals to 1, it'll reach this point. At t equals to 2 seconds, it'll reach this point. 3 seconds, it'll reach this point. Eventually, it reaches your ear, right? That's how we hear the sound, right? So the speed of the sound is going towards this person, right? Nancy, right? So Vs is the speed of the sound, okay? But what if we have a moving source of sound, okay? Now, instead of the source being stationary, I'm going towards you and speaking with the same frequency at the same time, right? So what happened is that, right, at t equal to 0, right, the sound is going to make a spherically outward wave, right? And that wave is going to reach Nancy, right, sometime later, right? The same, you know, whatever the distance divided by the speed of sound. But 1 second later, now that source is actually closer to Nancy, right? Since that source is closer to Nancy, oops, the green circle, right? The sphere, right, instead of being centered around 0, is now centered around 0.1, right? So this sphere is actually slightly shifted, okay? Since it has not had as much time to propagate outward, it is a smaller sphere, but you can tell that the difference between these two, the green and the red circles, are shorter because the sound source actually moved closer to Nancy between the time it emitted the first pulse and the time it emitted the second pulse, right? The third pulse is a similar situation, right? Where now the center of that sound, it actually emanated from this blue point, and the blue circle actually reaches here. You notice that, right? The distance between the blue, the green, and the red is shorter compared to the distance between the blue, the green, and the red behind the wave, right? This is the front of the wave. This is behind the wave. So if we think about these as kind of like each pulse happens at one wavelength, right? This one wavelength is shorter than the wavelength from behind the wave. So the wavelength that when the source is approaching you gets shortened, okay? Where the wavelengths that you are receding away or moving away from you gets longer, okay? We can actually calculate what this effect is because, okay, the speed of the sound stays constant, but the wavelengths get shorter or longer depending if someone's approaching you or moving away from you, okay? If I'm approaching you, the wavelength gets shorter, right? If I'm moving away from you, the wavelength actually gets longer, okay? This is known as the Doppler effect, and it applies not just to sound, but all waves, including electromagnetic waves. So you can actually, so this is an effect in astronomy where stars that are moving away from us gets red shifted. Okay, stars that are moving towards us gets blue shifted. Okay, so the speed. So starting with just this equation, that the speed of sound is the wavelength of the sound times the frequency of the sound, right? But now, right, what happened is that as the wavelengths get shorter, meaning, right, this gets shorter, the frequency is going to increase, right, as I approach you, okay? That's why as the train approached that observer, right, it had a higher pitch, okay? It created a higher pitch, right? So let's see what happens. See if we can figure out how to do this mathematically. Sorry, there's all these diagrams here that I pasted. So we don't have to do that. We talked about that. Okay. So, okay. So what we need to figure out is actually how much the wavelengths get shortened, okay, by just, the source of that particular train or me walking towards you is moving, okay? So we're gonna have two different speed, unfortunately. There's the speed of the sound, which I think we're just gonna use V without the S, okay? And then there's the speed of the source, meaning the speed of the train, speed of me, the speed of the star moving away or towards us, okay? So if you have a source, right, SRC, right, moving towards an observer, right, the change in distance that source is going to move over time, right, is actually going to be the speed of that source times what we're going to use the period of the wave, okay? Remember, the period of the wave tells you how many times, how long does it take for each of the peaks to reach each other, right, in time, okay? So that means as this source is approaching you, okay, the period, the amount of time it takes for the wave to repeat itself tells you how far and how much in time the peaks of these waves are going to be separated, okay? This is what we're going to quantify in this little diagram. Each of these pulses is one period apart, okay? Okay? Because we can't rely on the wavelength anymore because the wavelength is the thing that's changing on us, right? So each of these pulses, let's say this is, period 0, right? Period 1, period 2, period 3, okay? That's these pulses are coming out at regular intervals, right? Okay, and that's the period we're going to calculate. Okay, so that's the shift in distance, right? Because that's how far, right? At 0, it'll make a pulse this way, but then at 1, it'll start the pulse here instead, okay? So therefore, that means the wavelength is going to be shortened by this delta x, right? Okay. So if we want to figure out how much that the wavelength gets shortened, right? We just take the wavelength if the source is not moving, the regular wavelength that we're used to, right? Subtract that wavelength with this delta x, right? Whatever that is, okay? Okay. We have a calculation for that, okay? The wavelength of something, okay? If it's not moving, this is the not moving one. Oops, not moving. Okay. It's just the speed of the wave. I think we're just not going to use the wave thing, okay? Speed of the wave times the period of that wave, right? Because that's just using V equals to lambda F, right? If we solve this for lambda, lambda is going to be, go to the right. Lambda is going to be, what's lambda? V over F. And remember, F is just 1 over the period, right? Okay. So this equation makes sense. We plug that into here. We get that the first term is just the speed of the wave times the period of the wave. The second term we grab from up here, right? Because that's the change in the wavelength, okay? So we massage these equations a little bit more. You factor out the t, okay? Right? And let's see what we did. And then t is, of course, if you solve this equation for t, right, is lambda over v. How did I get from here to here? Oh yeah, there's lambda over v, okay? You plug that into here. So therefore, right, the wavelength, if you are approaching the object, gets shortened, right? This is the original wavelength, okay? This is the Doppler shift wavelength, okay? By this factor, v minus v source over v, where v is the speed of the wave, right? And v source is the train speed, okay? And you have to divide that by the speed of the sound itself, okay? So for things that are approaching you, the wavelength gets shortened. You can instantly tell it does get shortened here just mathematically, right? Because, right, v minus v source, right? Let's say the speed of the sound is 350 meters per second. The source is 50 meters per second. This will be 300, right? The denominator is still 350. So this is always a number that's going to be smaller than 1, right? If you multiply by a number by smaller than 1, you always get a smaller number, right? If you are moving, this is towards, okay? If you are moving away, okay? Similarly, the mathematics is basically the same. You just get a plus sign between the v minus, between the speed of sound and the speed of the source, okay? So when you add something to it, right, this is 350, and let's say the source is moving at 50 meters per second, right? You get 400 divided by 350, you're going to get a number that's always bigger than 1, right? When you multiply a number bigger than 1, you always get a bigger number, right? So hopefully that makes sense, where when you're moving towards the sound, your wavelengths get shorter. If you move away, the wavelengths gets lengthened, okay? But the wee woo sound comes from the pitch, right? Also known as the frequency of the sound wave, right? So you can actually convert this these two equations into frequency, and just due to the amount of algebra that might be involved, okay? The algebra is just converting. You can, if you know the wavelength of something, you can always convert to frequency, right? Because, right, the speed of the sound is always the same, where the frequency and the source, the product between them is going to give you the speed, right? So if you convert this, we won't go through all the algebra steps. What happens is that if you are going towards the source, okay, you get a higher pitch, and that factor is actually V over V minus V source, because, right, remember this idea that, well, the wavelength, if the wavelength goes up, right, the frequency has to go down. If the wavelength goes down, the frequency has to go up, right? So there's always this inverse relationship between frequency and wavelength. So since wavelength has this factor of V minus V source over V, right? Frequency will have the upside down version of it, okay? So therefore, if you are going towards the train, right, now you have a number, let's say, once again, right, 350 divided by 350 minus 50, right? So that's a number that's bigger than 1, okay? And you're multiplying by that, the frequency of the source, you're going to get a bigger number. Therefore, as the train approaches you, it'll have a higher pitch, the wee sound, okay? When it goes away from you, okay, you're going to have the woo sound, which has a lower pitch, and that's because the speed of sound is still the same, 350, 350. But then instead of subtracting, now you're adding, right? When you add this will become 400. So this will be a number that's less than 1. So you get a frequency that's actually lower, okay? Okay. And the book gives you this complicated formula to use. V of this S here for them stands for the source. So I actually like to spell it out, because S can either stands for source or sound, right? So like I would just everywhere in the book just write this SRC instead, okay? So this will allow you to calculate the Doppler shift in the frequency of the sound, okay? So do you have any questions before I do the example quick? Okay. So in this little example, what we can do is actually figure out how fast a police car is traveling by just listening to the sound. And you do the same thing in the worksheet today, okay? So we have a police siren, right, that's emanating at a frequency of 550 hertz. That's actually the frequency of the source, okay? Let's write that down as 550 hertz, okay? Right? Ooh, sorry. Frequency of something, let's not write the source yet. As the police car approaches you, okay? That's actually F plus, right? Because as it's approaching you, right, it gets a higher pitch. As it moves away from you, the pitch shifts to 450 instead. So there's a change of 50 from the regular, okay? And what the question is asking you, how fast is this police car traveling? Just by knowing the frequency of sound that it is making. Okay. It also gives you the temperature of the air. Okay. Why did the problem give you the temperature? To calculate what? The speed of sound. Exactly. Yeah. So the speed of sound, which is the one without the S, okay, is 331 meters per second times square root of, well, this temperature in Kelvin is going to be 293 divided by 273 Kelvin. Okay. So the speed of sound in this particular night is going to be 293 divided by 273, all square rooted, times 331. The speed of sound is 243 meters per second. Okay, that's the regular V without the S. Okay. So how can we figure out how fast the police car is traveling? Okay, we can pick either one of these actually. Let's do the F plus. So F plus, right, using this formula up here, is the frequency at this of the source. I'm going to do SRC instead of just S, multiply by, okay, the speed of sound divided by the speed of sound. Since we're doing the positive one has the minus, right? That's the confusing thing. Minus the speed at the source, okay? The speed of the source is the speed of the police car, okay? So I have to solve this equation for that. So if the police car approaching you has a frequency of 550, when it goes away from you has a frequency of 450, what is the actual frequency of the police car when it's not moving? What do you guys think with these two numbers? What's F source equal to? Anyone wants to guess? Any guess is valid. I'm sorry? You subtract them. That's the beat frequency, right? But if it's approaching you and it gains 50 hertz, and when it goes away from you, it loses 50 hertz, right? What is the actual frequency of the sound when it's not moving? 500 is the average of these guys, right? Exactly. Right. Okay. So we got this, we got this, we got this, we got this. So we can just solve this equation for V source. Okay. So V plus over, sorry, F plus over F source, right, is going to be V over V minus V source. Okay. Unfortunately, there's a little bit more algebra involved here, right? I have to multiply both sides by V minus V source. V minus V source. Okay. And that cancels this. I'm going to distribute this out because I want to isolate V source. V F plus over F source. I think I see why they just use S instead of SRC. Okay, because you have to write this a lot. Okay, minus V source F plus over F SRC. All that is equal to V. Okay, if I solve this for V SRC, then move that over, then you get V F plus F SRC. Put the minus sign here. Sorry, I'm going to do this in 2 steps because I'm confusing myself, right? F source plus V, right? And then you divide both sides by negative of all that stuff. SRC plus F SRC. Okay, now we have, come on, V SRC by itself, right? Because all that cancel out. Since we have a denominator dividing it by a fraction, that's the same thing as multiplying by the reciprocal. Okay, minus V F plus F SRC plus V. Same thing as multiplying by the reciprocal. Just want to make sure that I wrote that correctly. Okay. This actually cancels out with this stuff. Okay. Okay. The minus sign also cancels out with each other. So you just have V in front minus V FSRC times F plus. Okay. So all of that, we have all these variables. So the speed of sound was 343, and then F source was 500, and then F plus was 550, right? Just plug all that in. 5 by 550 times 343 with a minus sign, 343 without the minus sign. I got 30 meters per second. Okay, it's kind of cool. So you can actually determine the speed of the police car by just listening to it. Okay, hope I did that calculation right. Ethan, do you mind passing out the worksheet? You'll do a pretty similar calculation. Okay, I'm just going to double check because I punched my calculator. So 343 0 times 343 minus 343. Sorry, it's actually 31.2. Okay, actually punch in calculator correctly.